Hello, welcome to part 2 of my capstone project. For a quick overview of the main takeaways of part 1, I proposed a definition for timbre, which is the subjective interpretation of the relative amplitudes of the audible frequency spectrum and their change over time. I discussed thinking about timbre in a macro and a micro sense, specifically viewing the frequency response of any given sound, thinking about the macro level, so like the general contour, and the micro level, which is the shifting of the amplitudes of individual frequencies. And then lastly, I was wondering about finding patterns in either of these senses and seeing if those patterns could inform us as to why we perceive some sounds as being similar to each other, so grouping them together. And I used the example of the human voice. We can hear different people speak, and we can clearly tell who is who and discern them from each other, but we still think of their voices as being in the same group of sound as the human voice. So why is that? To try to answer this question, I decided to analyze some different sounds and their frequency responses. And my methodology was to choose arbitrarily just some different groups, and I wanted to get a pretty wide range, so I chose both pitched and unpitched sounds, or groups of sound. And then I wanted to get sounds that were clearly different from each other, but we still perceive them as being in the same group. So we'll see that the first group that I chose is clapping sounds, but within that I got a synthesized 909 clap, I had a clap with a lot of reverb on it, and I had a couple of acoustic claps, one of them recorded myself, just to see if it sounds similar. And all of these I would group as clapping sounds, but they sound very different from each other. And then I will analyze all of these with the frequency spectrum analyzer that we've seen in part 1, and specifically, just to let you know what I'm using, it's called Insight 2. It's by a company called Isotope. The reason I chose this one, I checked it against a few other ones, and I found this one to have a much higher level of detail. It was very accurate, and I could freeze frame the peaks from the sound. Even though I took short snippets and it changed over time, and Insight 2 can freeze frame the peaks, which I found very helpful. And then after analyzing these, I just wanted to see if I could find any patterns. So let's check out the first group. The first group that we have is clapping sounds, and I've taken away my face so that I don't obstruct the view of the frequency analyzers. I'll play each clap in order from left to right, top to bottom. A pretty good variety of sounds. The first one is the 909, second one sounds like it has a lot of reverb on it, and then the third and the fourth are very dry, and the fourth one is actually my own recording of a clap. Immediately, I feel like I can notice that the general outline of their frequency responses looks quite similar, but let's get into some smaller details. I noticed that all of them had 2 clusters in the mid-range that had higher amplitude on average than the rest of the frequency response. This is easier to see in the third and fourth clap, and I'm wondering if the synthesized nature of the first couple of claps may have something to do with the less defined clusters. The second thing I noticed was the general downward slope towards the high end. And then the third thing is this interesting trough in the extreme high end. It's at around 16 or 17K. I was curious as to why this was popping up in all of them, because it's not something I would have expected. It even showed up in my own recording. I soloed it out to see if it had any strong effect on the sound, but it didn't sound particularly unique to me. The last thing of note is that the range of amplitudes, so from the lowest amplitude to the highest amplitude among frequencies that are near each other, is relatively low. And what I mean by this is that there's not any strong resonances or deep, deep troughs except for that one in the high end. It's a generally flat response, but it still has a general outline that you can trace. The next group is bowed string instruments, and the first sound is a cello playing C3, the second one is a violin playing C5, and the third one is a violin playing C4, but it's pitched down to C3. So we can see that we lost that octave of information from 10K to 20K due to it being pitched down. Here they are in order. We can really hear in the pitched down violin that we've lost some of that high-end information. But I would still subjectively categorize it as a string instrument, a bowed string instrument. Immediately what pops out is the clearly defined harmonic series. These resonances are very noticeable as opposed to, with the clapping sounds, the small range of amplitudes. These very clearly have incredibly strong resonances all across the frequency spectrum. They do die down towards the high end, and it becomes a flatter response, but in comparison to the claps, it remains much more defined. An interesting pattern was this sort of cascading effect. We would have a strong fundamental followed by a general downward slope, which I would expect, but then it would reset with a new peak and then slope down again. And this happens a few times, and this is why I drew the arrows in, is to show where I noticed the new peaks and then the general slope down. So it's interesting that across a couple of different instruments and a couple of octaves, this pattern remains true. The third group is key rattles, and I chose this because I assumed going in that key rattling would be a relatively complex sound, being non-pitched and so dynamic. And what we're seeing here is not the 3 key rattling samples, it is actually 3 frames of the first key rattle sample. So we'll check out the other 2 afterwards, but here are the sounds in order. And that third one I recorded myself again. So in this first key rattle, we see that we have some lone resonances in the high mids, but then what sticks out to me the most is sort of this cluster of resonances at around 7K, and then an even larger cluster spanning from 10K to 20K. I think this is, I would imagine that this is what gives it its metallic sound, is this seemingly random grouping of strong resonances. And then it has a relatively flat response below 2K. For the second key rattle, this is perhaps a strong low-pass filter or a high shelf, cut out a lot of those high frequencies. But despite this, I've circled, we can still kind of see that there was a cluster between 10K and 20K, even though a lot of that information got cut out. We can kind of see it's still hanging on there for the first frame and then dies down as the sound takes shape. And we also see the strong cluster around 7K. This one is much wider. It spans all the way from 7K to 10K, with a few lone resonances circled again in the mid-range. This is my own recording, and same thing. 7K cluster, 10K to 20K, and then a stronger low resonance in around 2K. So it's interesting that that lone resonance popped up in all of them in addition to the clusters. After the key rattles, I wanted to get back to a pitched group of sounds, so I chose the human voice, which I would assume is also quite complex. These are male vocals. We're going to check out female vocals afterwards. And I have written the words that are being said or sung above the frequency analyzer. Here's how they sound.
Gang. Like me. Please.
We have a pretty good variety of sounds. We have different ranges of vocals, up high and in the mids. We have a strong plosive with the please, and a pretty strong onset with the word game. And despite all this variation, there's still a contour that we can see. We have the fundamental note in the low end, and it slopes downward. We can kind of see that harmonic series. But then it gets obscured a little bit in the mid-range with these 2 clusters. So we see the first one is right above 2K or around 2K, and it's a bit stronger than the second one, which is around 4K. And they're separated by either a deep trough or a dip in the peaks of the amplitudes. After those clusters is a general slope down in the high end, with maybe a little bit of variation in the shape. The female vocals had almost the exact same shape or contour. We have the low fundamental sloping downwards, the 2 clusters, and then the high end slope downwards. Let's see how they sound.
Can closed.
For the second one, for that word closed, we hear that it has some vibrato on it. And I was curious if that would affect the contour, but it really did not change it hardly at all. We can see a little bit of more resonances closer to each other, and that's probably due to the peaks in the surrounding frequencies. But the shape remains pretty true, which is interesting. Now, these are not the only female vocals that I checked out. The third one has its own page because I thought it was pretty interesting watching the analyzer in real time. So we'll find out why. So this is the word you.
You.
And let's check out what is actually happening. So it starts out the same way that we've seen all the other ones, but then if we notice, the first of the two clusters actually breaks away and moves downwards in frequency. So now that we know what to look for, I'm going to play it again and try to keep your eyes on around 3K. The first cluster is going to pop up, but then it's going to break away and almost in like 3 distinct jumps move down between around 1 and 2K. It's really interesting to see that happen. And I checked in tuning software to make sure the pitch wasn't going down at all, and it's not. There's the vibrato, but it hangs around the same note very strongly. And so what I believe is that this is the vowel shape changing. I think this is the vowel changing from the Y to the U. I labeled with a star the first cluster, and we see it start at 3K, move down, and then end up around a little below 2K, and it sort of morphs with the harmonics that were previously there. But the second cluster holds its shape really strongly. It sits at around 5K and it does not move at all. So this made me curious if I could track other changes in vocals. So I took a male vocalist, once again, saying the word do, and it sounds like this.
Do.
And the reason I chose this is because it has such a strong attack, and even though it happens so quickly, the clip can't be more than maybe 0.2 seconds or 0.3 seconds. But in the first frame, we see there's way more energy distributed across the frequency spectrum. There's much stronger resonances. The two clusters are a bit more obscured because so much more is happening. And then by the time he gets to the oo vowel shape, everything has calmed down. The clusters are much easier to see. There's less resonance between 1 and 2K, and everything is just a much flatter frequency response across the spectrum. This makes me think that we can track patterns for different changes in vocals, such as vowel shapes or plosives or attacks and things like that, using the contour of the frequency response. And so after doing all this analysis, I wanted to do something with it because I think it's fascinating to look at this stuff and find patterns, but I want it to be able to be helpful in some way. So how can it be used? I think there are two main things that pop into my mind when I think about how I would like to use this stuff. And the first one is organization. I think that there were clearly definable patterns among all of these sounds. The contours could be traced pretty easily, in my opinion. And my hypothesis is that for a lot of sounds that we think of as being similar to each other or being in groups, we can probably find patterns for them as well. That would require a lot more testing, a lot more research and analysis, but that's my hypothesis, just based off of the random selection I made here and seeing things in all of these groups. I believe that it's likely that we can find patterns in the frequency response of any group of sounds that we think is similar to each other. And I think that could inform us if we wanted to create categories of timbres. We can think of contours that are similar to each other and create categories of sounds that may be related in some way or another due to their frequency response. I think that would be very helpful for discussing timbre and discussing sounds in general. The second way that I wanted to use this research, I mentioned at the beginning of part 1, which is my own work, my own sound design. I want to be able to kind of reverse engineer it and use these patterns to create sounds or to design sounds. I'm going to play a clip, and I want to make it clear that I made these sounds using white noise, an EQ, and volume automation. Just these three things. And I made this with that. It's pretty cool, I think. It was really cool for me to be able to apply the patterns that I saw and try to create sounds that I felt would fit into these groups. So the things that I tried to create were a kick drum, a clapping sound, a hi-hat, some key rattles, which was way harder than any of the other sounds, and then like a super simple bass sound. And I thought it turned out okay. I think the crudeness of the sounds is to be expected based on my method of creating them with just the white noise and the EQs and the volume automation. It's not super surprising that they are very simple sounds and not particularly realistic sounding, but the implication is what I'm excited about and what I think can be useful moving forward, is using these patterns and perhaps a more sophisticated method of designing the sounds to create some really cool stuff in the future. And I want to say this research is by no means complete or comprehensive. There are a lot of sounds in the world, and there's a lot of testing and research to be done, but I think the possibilities are really exciting, and I think that there's a lot more to explore and a lot more to be done in the topic of timbre. Thank you.